Okay, today, there's the lighting. Lots of stuff we're talking about. Okay. So, last lecture, we pretty much finished up all the linear accelerator information I wanted to talk about. If you guys need more information on Linux, there's a really good book. I don't want to stack this course with a bunch of references because then you guys have to buy these books. But there's a book available in my library, and it's a, I can't remember the name of it, but I'll email it to you. There's just a lot of detail. There's two of them. There's the Karsmark. There's one by Karsmark, and then I think that was one of my references in the previous lecture. But then there's another one that's a little less. Karsmark is very physics oriented. There's a lot of math and physics in it. Then there's another one that's more qualitative. Okay, and that other book is a really easy read, and it really explains each component of the linear accelerator in kind of layman terms. Yeah.
So when you email us those, will you please email us the link also to the movie?
The link to the movie?
Yeah. You were talking about YouTube, something on YouTube.
Yeah. Oh, I didn't send it to you yet?
No.
Oh, okay. I'll send that to you. Yep. Okay, so today we're moving away from linear accelerators and we're going into the radiotherapy simulators, imaging modalities, breath management, and image guided radiotherapy. Lots of topics here. So let's get started. So first of all, simulation and the simulation process. So I know you guys have been going to Introduction to Radiation Oncology Clinic, and you probably have seen the CT sim. Right? A CT simulator. It's a CT scanner. Okay, that's a modern CT simulator.
What's it look like?
It looks like a scanner. It looks like you walk into the room and there's a big device with a hole in the middle and a couch, and the patient lies down and goes into it's a CT simulator. Okay. So before CT simulators, it was a different kind of simulator. But anyway, in terms of the simulation process, what's the purpose of this process? And where does it fall into the radiotherapy process? Do you guys have an idea where the simulation process falls in? Like what step? There's a lot of steps. The doctor first makes a diagnosis, then the patient comes to part. It's one of the first steps, isn't it? So the doctor sees the patient and says, well, you're a candidate for radiation therapy. These are our treatment options, and then the patient agrees to get treated. Then right after that, they make an appointment for the simulation. Okay. Now, before we had CT simulators, we had these things here, which are conventional simulators. And that's a really blurry image, but when I put my laser pointer, I brought it in. But so in a conventional simulator, it looks like a gantry. It looks like a skinny gantry.
Pockets?
I think I had it a second ago. Come on, laser pointer. Oh, here it is. It's dark in here. Okay, so it looks like, I might have a better picture of this on the next slide. I do. But anyway, here's a treatment couch, or a simulation couch, rather. Simulation couch. This is a gantry that rotates just like a linear accelerator gantry. This is an image intensifier, and then there's an X-ray tube up in the head. And the purpose of this, again, this is right at the beginning of the radiotherapy process. The physician lies the patient down on there and kind of strategizes how they're going to treat the patient. So they'll rotate the gantry and they say, I want to come in from this angle, and they can take pictures at any angle. So what I mean by a picture is a radiograph. There's an X-ray tube up here, and it shoots a picture. And what this does down here, the image intensifier takes the X-rays and converts them to light with a phosphor. So the X-rays get converted to light, and then there's a little camera at the back, and then that camera talks to a monitor. And that monitor is in the control room. So the physician, have you guys heard of fluoroscopy? Yes. Fluoroscopy is kind of online imaging. You push down on the X-ray tube pedal, and there's X-rays coming out. You can see the patient move, so it's online. It's not a radiograph. A radiograph is a snapshot in time. A fluoroscope is dynamic. Okay, so the doctor with fluoroscopy sees the patient's anatomy, and they can move the couch around, turn the gantry around, and that's how they determine what angles they're going to come in to treat the patient with. Okay, and then when the doctor likes the angle, for example, if the doctor's treating prostate, so they'll see the pelvis up here, ischial tuberosities down here, Okay, should tuberosities, and the sacrum is down here. And so the doctor wants to treat the prostate, so the prostate's over here. So the doctor will place that gantry in the AP position, which is in the 0 position, pointing straight down at the patient. And then they can put the crosshair, they can center the crosshair on the prostate. So they want to, again, we're treating prostate. They can center the crosshair on the prostate. And also, there are these things called delineator wires up in the head of the simulator, up in here. And those can move around, not move around, sorry. They move left and right and up and down. And then those wires designate the field size. Okay? And then once they have that set up, in terms of how big they want to treat, the isocenter, bing, they take a picture. Okay, they take a radiograph of that. And that radiograph, we put a film in this cassette holder. Okay, have you guys seen cassettes? What a cassette looks like? It's a kind of a rectangular, flat rectangular piece. You can open it up, and you put a piece of film inside, and you lock it shut. Okay, so you'll see those. They're not that common today because everything's gone digital. But basically, a cassette is what holds the film in. Okay, so we would put a cassette in here. After we take the radiograph, take the cassette over to the dark room, and we process the film. Okay, so then the doctor with those films, and those are called sim films, simulator films. This is a bit of a history lesson. By the time you guys get out in the field, you won't have too many of these around, but this is just a little background. So you'll have, because everything's CT based. So they take the simulator films, and on the films, the doctor takes a pen and draws what they want to block. So in this case, the doctor might want to block this, and want to block this, here. You might see these films. I mean, you might pull, when you work, you might pull some films from old files, and say, what the heck is this thing? You know, it's a film, and there's, you know, you can see the pelvis on there, and you'll see these lines that the doctor drew, and then the doctor draw these blocks. And in the days of Saraband, we would take these films, put it on the block. Have you guys seen the block cutter yet?
Yeah.
Okay. They put it on the block cutter, but with the block cutter, they'll trace out these blocks. Okay, they'll put the film down on the, of course it's down flat horizontal, and the pointer is pointing this way, and they'll trace these blocks out. Okay, and they'll cut these holes in pieces of styrofoam, and then we'll pour Saraband in here. Okay, and when that hardens up, these get mounted onto an acrylic tray, and that tray gets mounted into the head of the machine. Okay, and then these block the radiation. In the days of MLC, it's a lot easier. You could take this film and digitize it on a digitizer, or on you could digitize it and put it in a computer, and then with the mouse, you draw these films out. Sorry, you draw these blocks out. And then that goes to the MLC computer, and the MLC brings the leaves in to where they're supposed to be for treatment. No need for Saraband blocks because the leaves are programmed by the computer to move to a certain position for each field. Okay, does that make sense? So that's what a sim film does. So let's go through these bullets. And the simulation process basically is to acquire all these simulator films. And that's number one. Acquire simulator films. 2, make a mobilization device, and we'll talk about that. 3, mark patient's isocenter. Mark patient's isocenter with marks that they don't remove until they come back for treatment. And basically, they keep the marks on for the whole course. So these are the 3 main steps.
So what?
So the first one is to acquire the simulator films.
Yeah, but it's the first 3 steps too. Well,
oh, to the simulation process. Yeah. Okay. And the acquiring simulator films, basically you're setting up your treatment fields. Okay, that's what you're doing. Setting up treatment fields. Okay. And then, so, number 1, simulator films and setting up treatment fields. Number 2, make a mobilization device. Number 3, mark patient's isocenter. And this should actually go up here. The order is not right. The mobilization device would be first, take your sim films, and then mark a patient's isocenter based on where the physician put the isocenter. Okay? Those are the three main steps in the simulation process. So a patient is placed in the treatment position, and the mobilization devices are selected. Okay, so if you're treating a patient for breast cancer, there's a special kind of mobilization device called a breastboard. Okay, and we can go into those in a little more detail in a minute here. Then films are taken that correspond to treatment films. Beam blocking is drawn on films by the physician. Blocks or MLCs are constructed or digitized. Films are later used to compare to portal radiographs, and I'll talk about that in a minute. Patient contour is taken using lead wire. This is old. This is really old. This is before CT scanners were around, and this is when I started in this field. This is what we did. The patient would lie down on the table, and the dosimetrist or the physicist would come. Have you guys seen solder wire?
Yeah.
It's kind of soft wire, right? So we'd use this thick solder wire, and while the patient's lying on the table, after the doc has placed the isocenter and the marks are drawn, we come in, and the last step is to put the wire, if we're doing pelvis, put the wire around the pelvis, and then we lift the wire very carefully, and we put it on a big piece of tracing paper, and we tape it down, and we draw that contour. And that's what we use for our treatment plan. Just one simple contour around the patient. And then we digitize that into our treatment planning computer, and then we put the beams on, and the computer just had that one contour, but it was able to calculate the doses in that one contour. That's called 2D treatment planning. Okay. So that's really old. It's important for you guys to know it, the background, but we don't do that anymore. Then the patient is marked with ink or tattoos that don't come off, so the position can be reproduced in the treatment room. Okay, so they're marked with we call this a 3-point mark. One mark on each side and one mark on the anterior surface. And those all intersect at one point. Okay? And that's the isocenter. All right. So that's another one. That's another view. This is called the Varian Zimatron simulator. And again, this is an X-ray tube up here in the head. And it's not an X-ray tube, but there is an X-ray tube up here in the head. This collimator rotates just like a gantry collimator too, because if the physician wants to rotate the collimator, you have to be able to do that in the sim. And this image intensifier takes the X-rays, and basically the way this works, and you'll learn this in diagnostic radiology, of course, an image intensifier is made out of a photocathode. A photocathode takes photons, which are the X-rays that come from the X-ray tube, and converts them to electrons. Okay? So it's a special material that converts photons into electrons, so it creates a lot of electrons, and these guys are now in an electric field. These guys experience an electric field, and they get focused down. In this electric field, they get focused down to a point, and they hit a CCD. They get focused down to an area like this, and they hit a CCD camera down here. Okay, and that CCD camera, then the image from that CCD camera then goes to the monitor that shows the pelvis or the patient, whatever you're imaging. Okay, that's a bad picture of a monitor, but this monitor is in the control area. Okay, so basically the II takes the X-rays, converts them with the photocathode, converts them to electrons. The electrons are focused down to a CCD camera, and the CCD camera, you know what a CCD is? A charge coupled device. It's just what's in your video cameras. And then that gets displayed on the monitor. Okay, and then you could turn on the X-rays, and then this monitor will show you. It's basically a fluoroscopy unit, so this monitor will show you what's going on in the patient's anatomy. These have pretty much been replaced. This is called an image intensifier. They've been replaced with amorphous silicon plates. So over the years, they've been replaced by amorphous silicon plates, and the amorphous silicon plates are digital imaging plates. They're a lot smaller and flatter, and they just create these X-rays into a digital picture. Okay. So there's some background on that. And this couch is pretty much identical to the couch that the patient's treated on. There's another really old piece of equipment up in there. Do you see it? TV? Yeah, CRT. Don't see those anymore. Okay. Okay, so those are the older simulators. Some sites still use them. You can still buy them. Varian still makes them. The newer simulators, let me go back one second. The newer simulators, they'll rotate, and the imaging plate over here will capture a CT scan. So it's basically, it can create a CT scan. Okay, Okay, so they've gotten modernized, but most people use CT scanners for the simulation.
And these are all just pictures, right? They're not the real-time like the fluoroscopy you said.
These here?
When it comes to the monitor, is it a picture or does the patient move?
You mean this monitor right here?
Yeah.
This is for fluoro. This is for fluoroscopy.
So when the patient moves, it moves on the monitor as well.
Yeah. So you can see. I mean, you can see patient breathing and movement. I mean, the purpose is not to see the movement really. It's just to be able to turn the gantry and see real-time X-rays as you're turning the gantry, as you're turning the collimator. It's just to be able to take a. Because you don't want to run a film every time you turn a gantry and you say, well, I want to turn a 5 degree. Let's try a 5 degree change. You don't want to go run a film or process a film all the time. So this is just real time. It's basically real time X-rays. That's the advantage of that. Okay, so then we move to CT scanners. And CT scanners, I don't know how much you guys know about CT scanners. You'll learn a lot more in your diagnostic course. But CT scanners consist of a couch and a gantry. Now this gantry doesn't turn because what turns is inside the gantry is there's an X-ray tube that spins around. And as the X-rays go through the patient, there are detectors all the way around it. And those detectors create images on a slice-by-slice basis. Okay? So these are just some examples of some cuts through the brain. Okay? And CT scanners is CT stands for, what does CT stand for? Computed tomography. Okay, so tomography comes from the Greek word cutting. Okay, so we're cutting through the patient. This is an example of we're cutting through the brain. So computed tomography. Okay. And this is a joke. We've given you a brain scan. We can't find anything. That's good news or bad news. Okay, so CT sim process. Now we're moving into more modern simulators, which is the CT-based simulators. And this is another blurry picture of a CT scanner, the couch, patient, and the patient's got her arms up in a breastboard. Okay, I think the next slide has a breastboard in it, a better picture of a breastboard. So this is a CT sim process. This is the radiation therapist setting up the patient on a breastboard. So the patient is CT scanned in the treatment position and in an immobilization device. The images are acquired through the treatment area. The CT slice thickness ranges from 1 millimeter to 5. The most common one today, I would say, is about 3 millimeters. The disadvantage of doing 5 is that your images are kind of choppy. Okay, so if they're 5 millimeter thick, the resolution's not as good. If they're 1 millimeter thick, the resolution's really good, but the patient gets more dose. It takes longer to scan the patient. Then the physician can place the beam after the CT scan's been done. The physician looks through all the slices and decides to place the beam isocenter on a particular slice. They can do that. Then inside the room, there are some lasers that move. Have you guys seen the in-room lasers? And I know you've seen them in the treatment room, but they're also in the CT simulator room. And in the CT sim, they can move. So the horizontal lasers can move up and down, and the vertical lasers can move in and out. So after the doctor places the isocenter on an image, that computer talks to the room lasers, and the lasers can move to the isocenter.
Automatically?
Yeah. Okay. And then when the lasers move to the isocenter, the therapist can mark the patient there, and that's where we're going to put the isocenter for the treatment machine. Okay. CT images are then sent to the 3D treatment planning computer via the network. Okay. And usually the treatment planning computer is not in the simulator room. It's back in physics or back in dosimetry. So those images have to get sent over the network. The patient may also undergo an MRI and PET scan, and images will be registered fused with CT. So MRI is magnetic resonance imaging, and we'll talk about that in a few slides here. And PET scans are positron emission tomography. Now, just a quick overview. MRI is for imaging soft tissue. So basically, MRI gives you soft tissue contrast. CT gives you contrast between soft tissue and bone and air. But MRI brings out the contrast in the soft tissue. All right. So in a CT scan, it's hard to distinguish the brainstem from the rest of the brain. Just as an example, it's hard to distinguish vessels from the rest of the brain. It's hard to distinguish abnormalities in the brain from the rest of the brain. And MRI, it's really good. MRI is very good for distinguishing slight changes in contrast within the soft tissue of the brain. PET scans, positron emission tomography, is for function. Now we're looking at what is happening in the brain. What's the metabolism in the brain? Or it doesn't have to be, I keep saying brain because we were just looking at a couple of brain scans. It could be anything in the body. Okay. And then once these images have been acquired, MRI or PET or both, we can fuse them with the CT. And I'll show you what fusion is about in a second. Okay, and this is a breastboard. So this is an example of a mobilization device. You guys might have seen these already in your intro class. So a patient that has breast cancer would lie down on this device. The angle changes, so they can change the angle depending on how the doctor wants to set the patient up. These are arm supports, and they could be, there's numbers and indices on here, and they can be set to any position. Excuse me, and that can be recorded in the patient's chart so that when they get there for treatment, they can be dialed in for each day. Okay, so the purpose of this is to set the patient up the same way each and every day, and also to keep the patient from moving. And this is a different one. This stuff right here is called alpha cradle. Have you seen this? These bags.
It's the vacuum sealed stuff, right?
Well, there's two kinds. The vacuum. There's a vac lock bag, and there's alpha cradle. I'm really sore. I did weights yesterday, and I'm dying. Okay. So there's a vac lock, and so you guys might have seen that. That's a bag full of these little foam BBs. You plug a really high-powered vacuum to it and suck all the air out after the patient lies down on it, and that form is maintained. And basically, that form should stay for the whole treatment, for the whole 2 months or whatever they're there for treatment. So that's vac lock, and then there's alpha cradle. Now this stuff here is made with two chemicals. It's an epoxy type material, and that's what this is in this picture. They place a bag that looks like a garbage bag, and then before the patient lies down, they pour this chemical. Well, first of all, they take these two chemicals and they mix them together and they shake them up, and it creates a reaction. Then they pour this mixture inside the garbage bag. They close it up with tape and they spread it out evenly, and then the patient lies down on there, and that foams up. So the chemical reaction creates this foam. That foam bubbles up around the patient. Once the foam sets up, it becomes pretty hard, and it's light because it's foam. Okay, so it's light, you can carry it easily, and it forms. It usually does a better job forming around a patient than the vac lock, but it can get really messy. If you spill this stuff, it doesn't come off. I mean, if you spill it on the table, it won't come off. You'll be able to scrape the big stuff off, but all it leaves a stain. So it's messy, but it forms really well. And in the long run, it might be more expensive in the long run because you have to keep buying this material. With the vac lock, you just reuse them. Okay. So get back to CT simulators. So the CT scanner is a scanner used mostly for diagnostic imaging, but in radiation therapy, there is a special scanner called a big bore scanner, or a big bore, large bore scanner. And these scanners this hole is bigger than a regular diagnostic scanner, and it's bigger because we need to put the mobilization device inside, like the breastboard. And also, if the patient's at an angle like this on the breastboard, they're elevated, so they might not fit as well. So they created these big bores. That's one reason. The other reason, so two reasons for big bore. One, immobilization device. And two, we need to include entire patient external surface in scan. In the scan. Okay, so in a regular diagnostic CT scanner, the field of view, after you look at a CT, you'll do a CT scan, and say you're doing something to the pelvis. So femoral heads, you're looking at the femoral heads, and ischial tuberosity is over here somewhere. And the patient's skin is out here. So we have a large patient. Now the field of view in a regular diagnostic CT scanner cannot encompass the entire patient. It's just not big enough. So the field of view, what you're actually seeing is something like, it's usually circular, and it's something like this. Okay. And that might be okay for diagnostic purposes because nothing's going on in here, like for prostate cancer. Nothing's going on out here. So the radiologists are okay with just seeing the inside of the patient with the prostate. Now, that's not okay for radiation therapy planning. When we're planning, we're going to be designing, we're going to be calculating our isodoses based on beams that come in from different directions. And if the treatment planning computer doesn't know what's beyond this dotted line, it doesn't know how thick the patient is. So it'll misinterpret the depth of the photon. Okay? So we need to encompass the entire pelvis inside the field of view to be able to have this external surface out here for treatment planning. This is for treatment planning purposes, because we need to know the exact depth, the entire depth for our calculations. Okay, so if we're gonna put treatment fields on the patient on a treatment planning computer and calculate isodoses, if we only have part of the patient, the depth is going to be shorter, or it's going to be less than we think it is. Okay, so the big bore scanners give us a bigger field of view. So the field of view of big bore scanners is bigger as well. So we encompass the whole external surface of the patient. So those are the two main advantages: to fit the mobilization devices and to include the whole external surface of the patient. And this is what a CT scanner looks with the covers off. There's an X-ray tube up here, and there's some solid state. They're hard to see, but there's some solid state detectors down here. All this junk in here rotates around. Everything rotates around, and the electrical obviously the X-ray tube needs high voltage, and those electrical contacts are built. They're like flat contacts. It's kind of like a track. One track makes contact with another track, and so as they rotate around, there's no cables rotating around. It's just tracks that are in contact with each other. Oh yeah. Little animation. X-ray tube, solid state detectors. Okay. Multi-detector CT scanners. Now, a single detector CT scanner creates a slice for one rotation of the X-ray tube. So for many years, as the tube rotates one time, one rotation equals one slice. So that was the rule for many years. Well, they found that, and so as the tube rotates, there are detectors, or one row of detectors. I'm trying to draw a 3D here. Okay, so there's one row of detectors, and so as one rotation, these detectors create one slice. Now, over the years, they found that they could do a much quicker scan if they could place more detectors in here. So they started placing two detector rows, 2, 4, 8, 16. So as they do that, that means that if you have an 8-slice scanner, for one rotation, you have 8 slices. Okay, so it's a lot quicker now. You don't need as much tube heat, you don't load the tube as much, you can produce a quicker scan. That doesn't say scammer, it's scanner. Okay? And so the dual detector came around in the 1990s, and then there was a quad detector, 4 detectors in a row, so 4 slices per rotation in 1998. Now we're up to about 320, and they keep adding more detectors. So 320 slices in one rotation. So a lot of patients can get scanned with just one rotation, because that covers the whole rotation area. Okay, so they lie down and they get scanned in like a millisecond. Now this is starting to be called, some newer CT scanners do what is called a cone beam, CBCT, a cone beam scan. The older scanners were single slice, which means that the X-ray tube is up here, for example, and the fan beam of X-rays extends this way, but the thickness in this direction is one slice. So it could be 1 to 5 millimeter. Okay? But now with cone beam, what they're doing is they're extending this into the board, so you can acquire a larger area, like 1 foot or 2 feet wide in this direction, into the board direction. Okay, and that's called a cone. So now it's looking. The older scanners were like a fan beam. It was a flat beam of X-rays. Now they're wider, and they're calling that a cone beam because it's like a cone of radiation. And all these detectors are picking up the signal, the X-ray attenuation. Okay. I mean, I'm just giving you guys an overview. I don't want to go into too much detail because you'll be learning about CT scanners in your diagnostic course. This is just an overview since we're talking about CT simulators.
Well, so, question.
Yeah.
What does the S stand for in OSCT?
Multi-slice CT scanner. Oh yeah, that's right. I wrote multi-detector and then I write multi-slice. Yeah, it's the same thing. Multi-detector, multi-slice CT scanner. All right. So now with all these slices, now we could do 4D CT. Now what 4D CT is, we're adding another D. So we started with 2D, then we went to 3D. Now we're doing 4D, and what's the fourth D is time. Okay, so we could do a CT scan of a person and look at the scan at different points in time. Why would we want to look at different points in time? For example, if you're doing a leg and you do a leg and then you scan it again, it's going to look the same as long as the patient didn't move. But if you do a lung and you scan it and then maybe 10 milliseconds later you scan it again, 10 milliseconds later you scan it again, scan it again, scan it again, they're going to look different because the patient's breathing. Okay? And that's what we want to do. These days we want to capture patients' breathing. We want to capture tumor motion. We want to capture, in cardiac studies, we want to capture how the heart beats. Okay? And those are called gated studies. So with these quicker CT scanners, we can now capture 4D CT. So we can have entire CT scans for every cycle of the breathing cycle, for example, every portion of the breathing cycle. So the 4D CT advantage is advantageous for lung, upper abdomen, or peristalsis, where much movement exists. And then this will lead into breath-gated radiotherapy. And I'll talk about that in a couple of slides. Okay, does that time component make sense? Okay. Okay, and then just a quick overview of CT numbers. What is a CT number? CT number is also known as a Hounsfield unit. Down here, Hounsfield units. This and this mean the same thing. CT number and Hounsfield unit, same thing. And a CT number is the equation for a CT number is equal to, this is a mu, the Greek letter mu. It's the linear attenuation coefficient of tissue minus the linear attenuation coefficient of water divided by the linear attenuation coefficient of water times 1,000, and that is a CT number. Okay, so after you do a CT scan of a patient, you can have these little tools and you put it anywhere on the patient. You'll just see a bunch of grayscales. We put it on the grayscale and it'll tell you what the CT number is of that scanner. Okay? And what's the purpose of CT number? Basically, it's telling you the attenuation density of what you're looking at. It's not physical density, but it's attenuation density. Okay? So mu depends on, and I know we covered this before, it depends on the density of the patient, the atomic number, and it also depends on the energy of the radiation. So in this case, the energy of the radiation doesn't change too much in a CT scanner. It's usually 120 or 140 kV. So it's mostly the density of the patient and the atomic number. So for materials that are metal, for example, on a CT scan, you're going to have, this is going to be really high because it really attenuates. Okay? So this is going to be high minus the mu of water divided by mu of water. So basically it's a big number minus 1 times 1,000. So the CT number of metal and bone and high Z material is going to look white. It's going to be a high CT number. And this is the range right here. So down here, air. So lungs are going to be a minus 1,000 CT number. Okay. Water is going to be 0. That's the definition of the 0 Hounsfield unit. It's defined for water. Fat and bone they're all pretty close. Bone's about a couple of hundred. Oh, sorry. Bone's about 1,000. It's up over here. And then up here is dense bone, 3,000. That's really dense bone. Okay. Just an overview of CT numbers. Okay. Now, DRRs. DRRs are digitally constructed radiographs. That's what DR stands for. And DRRs is a byproduct of a CT scan. And if you look at a DRR, you'll look at a DRR on a computer screen, and you look at a radiograph, like an X-ray, they look like the same thing. But they're constructed differently. They come from they're made differently. Okay? Like an X-ray, a basic radiograph, here's an X-ray tube up here, so you've got the anode up here and filament, and you've got your patient lying down, and then you've got a piece of film. This is a patient, by the way. Okay? And it looks like a dog, but it's a person. And the X-rays come down, and they irradiate the patient, and you get what we call a transmission radiograph. Okay? It's a transmission of the patient's anatomy, and you're getting a radiograph, and the X-rays, actually the anode's over here. Anode. And you get a radiograph. Okay, and these X-rays, they come from the anode isotropically, right? They go in all directions, and they diverge in all directions, and they hit the X-ray, and you end up with an X-ray that represents the attenuation of the patient. Okay, a DRR, a digitally reconstructed radiograph, comes from a CT scanner, and the CT scanner, we're going to change this diagram a little bit. In a CT scanner, there's a patient. The patient's lying down in a CT scanner now. The detectors are acquiring the information, the transmission information, slice by slice. Okay? And once all these slices have been acquired, we now have like a representation of the patient on a slice by slice basis. Okay, so the computer knows, and if I turn this around, it would look like that. If I turn this is just it would look like that. So imagine one of these, but they're all stacked up like this. Okay? So this is a brain with all the slices. Now we don't want to bring the patient to the X-ray room and take an X-ray, because we still need a radiograph to compare the port images, and I'll explain that in a minute. But we don't want to take the patient to the X-ray room, so we can use all the information that we require in the CT scan to create a radiograph electronically. And it does this all in the computer. So the computer imagines where the isocenter is, because you've placed an isocenter in the patient somewhere. And then it knows where the source of radiation on the linear accelerator is, because that's also been entered as information in the computer. And with that information, it draws ray lines through its computer. It draws ray lines through the CT, through each CT slice. And remember that these slices have already been acquired, and all that attenuation information, all these grayscales, represent attenuation. So this is bone. So as it's drawing, you can't really see this line, but this is the ray line that it's drawing. And it knows that there's bone here, this is soft tissue, there might be some air or some fluid here. And so it adds up all the attenuation coefficients, all the mu's, and puts an average mu right here in this pixel. Okay? And it does that for a two-dimensional film. So here's the film. It's not real film, it's just a digital film. So it does this in 3 dimensions. And then it shows it to you on a two-dimensional, I'll have it on the next slide, in a two-dimensional representation. And that corresponds to a regular X-ray. Okay, so that's a DRR, digitally constructed radiograph. The computer places all these ray lines and computes the average attenuation coefficient through the ray lines, and places that average attenuation coefficient as a pixel. Okay? So a ray line is traced through all CT slices, and the photon attenuation is calculated from the sum of all CT numbers. This gives us great control in how the DRR is displayed. For example, we can have the ray lines ignore all but CT numbers that are associated with the bone. So if you want a DRR and it just shows you bone, you're going to tell the computer, ignore all this soft tissue and just show me the bone. And then you're going to see just bone. Okay? Or you can say, show me everything, and then it's up. Then you could window and level it, and I'll talk about window and leveling too, to see what you want to see. So do I have a picture of a DRR? No, I don't. A DRR basically looks like an X-ray. Okay, so that's a DRR. So again, a DRR is calculated to be similar to port films or sim films by using isocenter to center the image. DRRs are used in 3D treatment planning to set the field size and draw blocks and multi-lead collimators. Okay, so kind of like before when I said when we did the simulation and the physician drew blocks, well now the physician is going to draw blocks on the computer screen from the DRR. Okay, so that's kind of like the new X-ray. DR is a new X-ray. Up here, there's a faint image of a scout image. Now, there is a difference between a scout image and a DRR. And when the patient's first CT scanned, the first thing that they do is they do a scout image. Okay? Now, a scout image is an image that you get by moving this patient through the CT scanner with this slice coming down, and what it shows you is basically through this fan beam a projection of the attenuation of the patient as the patient's sliding through. Okay. Now that image, that's an example of a scout image right there. It kind of looks like an X-ray. It could be a DRR, but it's different. It's different because as the patient moves through in this direction, the X-rays are coming down through the patient. They're not divergent. Look at this. This is a fan beam. Okay. It's not a cone beam. It's a fan beam. So you're creating an image where the X-rays don't diverge in the head to foot direction. There's no divergence in this direction. There's only divergence in the left to right, in the patient's left to right, because it's a fan beam. Okay, so what happens is that you have no magnification in the head to foot direction. Okay, and that would look different than if you're gonna take an X-ray. It's hard to draw in 3D, but if you take an X-ray of a patient, there's a source, and there's a patient. The source emanates. The X-rays emanate in all directions. So objects that are close to the source are going to get magnified in all directions because the X-rays emanate in all directions. But if you have a fan beam, objects that are closer to the source get magnified only in the direction of the fan. They don't get magnified in the other direction. So it's a distorted image. Okay? And it doesn't really look all that distorted, but it is distorted because there's no magnification in the head to foot direction. Okay? So it's something that people ask all the time, and you'll see these in board questions. They'll say, explain the difference between a scout image and a DRR. Because somebody might send over a scout image to the treatment plan computer instead of the DRR. And so you guys need to understand the difference between the two. And it would be inaccurate. So the measurements wouldn't be accurate on there, and the blocks wouldn't be accurate. Okay, so scout image or scout film from a CT is not a DRR, and it does not diverge in head to foot direction due to fan beam geometry. Okay. Any questions? Because I'm kind of moving really quickly through these topics. I don't want to lose you guys. Are you doing all right? Okay. You can always think about it at home and then email me. Okay, so why are we acquiring DRRs and sim films? I keep saying we're going to take this film or we're acquiring. Do you guys know why we're taking these? Why these DRRs and sim films are important? And I did mention one thing. You put the isocenter on, you draw the blocks. What are we going to do with these? Did Theo and Joe talk about the purpose of sim films and DRR films? What is it? Oh, who's going to look at them? Yeah, oncologists and physicists are going to look at them. But the ultimate purpose of these is to compare with a port film. You guys heard of port films? A port film is a film that's made on a radiotherapy accelerator that shows you the shape of the blocks and it shows you where the isocenter is on a patient. Okay, and that's what this is. Port films aren't very clear, and they're usually a little bit blurry. Why do you think they're blurry? Why are they blurrier than that? Look how sharp that is. Why would that? Of course, it's a different area of the body, but
because you're using MV.
You're using MV, okay? And so the problem with MV, and the reason MV doesn't give you contrast, is because the energy is so high, okay? And so all the photons scatter equally, and so they don't give you any contrast. So you're using MV, so it makes it blurry, but still you can make out some anatomy. So you can make out lung in this case, and right here you see the airway. This bifurcation right here is called the carina, so we use that a lot as a landmark. So what we'll say is, okay, well, the doctor will look at this and say, well, it looks like this edge is, you can take a measurement tool and say, it's 3 cm from the carina. And then they'll look at the DRR and they'll verify that it's the same, that the measurements are the same. Okay, so, and so this is important because all of our planning is done on the DRR. And then when we treat the patient, this is actually what we're treating with. So we want this to look like our DRR. Okay. So the DRR, I don't have a DRR in this example, but the DRR is just going to look like a sharp version of this. But so again, the purpose of the port film is to verify that the blocking is correct. You see how the MLCs are entered? That the blocking is correct. We're blocking what we want to block. And that you don't see the isocenter on here, but you're also verifying that the isocenter is in the right place. And you're comparing your port film to your DRR. Okay, so the DRR comes from the plan. So the DRR is intended. DRR intended treatment. TX is a abbreviation for treatment. Intended treatment, and comes from or is generated by treatment planning computer. Okay, and then a port film. Port film is actual delivered treatment field. Okay, it contains isocenter and blocking information. So we're talking about sim films, what they're for, how they're generated, how DRRs are generated, and port films and what port films are for. And now we're going to move on to respiratory gating. And I said that 4D-CT lets you capture the movement of the tumor. So in radiation therapy, the most important reason to use 4D-CT is for lungs. It's to see where the tumor's moving. Okay. And so in the old days, before we had any kind of 4D-CT or fast scanners, we would say, well, this patient has lung cancer, we could do a CT scan and we can kind of see where the tumor is. I mean, it's not that obvious, it's kind of blurry. So we'd see where the tumor is, and the doctor would put a big margin on it. And say, well, I know this tumor is going to move maybe up to 2 centimeters due to breathing. So I'm going to put a 2 centimeter margin, and I'm just going to treat this big block of tissue. Okay, but I know I'm going to hit it. Okay, but that's what I want to do. I want to make sure there's no recurrence, and I want to hit it. But the problem with that is that you're hitting a lot of things you don't want to hit. I mean, you're hitting core, esophagus. There's nerves in there. There's all kinds of things. Liver, it could be down to the kidneys and liver level. There's all kinds of things you don't want to hit. So over time, we want to shrink those margins. Well, how do we shrink those margins? Well, we can shrink those margins if we know where the tumor is in time. Okay. So this slide here is a nice slide, which, if you think about it a little bit, there's a lot of information in it. These lollipops right here represent the tumor. Okay? So this is the tumor. This round thing right here is the tumor. And the tumor, as the patient, this is time. 1, 2, 3, 4, 5, 6, 7, 8. These are cycles in time, or time intervals. And so this tumor is moving down, and then it goes up, and then it comes down, and then it goes back up, right? Now, as the patient's being scanned, the patient's lying on the couch, and the CT scanner is going around, and the couch is moving in, it takes a slice, moves in, takes another. We're thinking about a single slice scanner right now. Moves in, takes another slice, moves in. While it's doing that, the tumor's moving up and down. Okay, so, as the tumor's moving up and down, and see these slices? This is the couch position. One couch position, then the next couch position. It looks like they're really thin, like a millimeter apart. Next couch position, next couch position. So you're going slice by slice by slice. Meanwhile, the tumor's doing whatever it wants. It's kind of just moving around. And so this is what the CT slice would look like. If you're looking, but it's not like a 2D slice, it's a 1D slice. And so in position 1, this corresponds to position 1, you're clipping the top of the tumor. Okay? Then in position 2, because the patient's exhaled, even though the couch is moved up, you're missing the tumor. Position 3, missing the tumor. Position 4, patient's about to inhale. Now you're clipping the top, so this looks like that. Position 5, patient's inhaled and it's all the way down here. Now you're clipping the bottom of it. Okay? Position 6, patient's starting to exhale again, and it's coming out of the slice again. And so the tumor should look like that. I mean, we should see a circle, but it looks like that. Okay, that's terrible. So that's what we've got these days with slow scanners and single slice scanners. This is what we have to work with. Okay, so you can see why there's a need to go to 4D to get information about the temporal or time information about the tumor. You guys understand this? How this works? Okay. Okay. Now, 4D CT. What's 4D CT? Oh, here. Let's see if I can get this movie to work. I might have to. Well, let's just try it. Sometimes it has trouble with that because it's recording. But this is a really good. It's a really nice movie of that. Have you guys seen it, by the way? Have you downloaded the? Did you give it a try? Okay. Come on, you can do it. I have to pause the recording. I'm just going to pause the recording. We don't need to record this. So you can watch that movie at home, but it's a movie that shows, it was taken with a 4D CT scanner. It shows the lung moving up and down and how the tumor moves. So here's how a 4D CT works. So a 4D CT, think of to make it simple, think of this is a 4-slice CT scanner. So, where's my pointer? Okay. So this is up here. This is the patient's breathing cycle. All right, so the tumor is up here, and then it comes down, and it goes back up, comes back here. Second table. So first table position means the table's set in one position. All right, and then the tube spins around the patient, and as it does one rotation, it grabs 4 slices. Okay, because it's a 4-slice detector. So if the scanner is set to a slice thickness of 2 millimeters, how thick a scan is it getting? 8 millimeters. Okay, so it's getting 8 millimeters, about a cm through the. Is this a brain or a pelvis? I don't know. It kind of looks like a pelvis here. That could be, or a heart. This could be the heart. So it's going somewhere through the thorax, and it's getting 8 millimeters worth of data in one rotation, but it's getting 4 slices. 2 millimeters, and then there's another one next to it that's 2 millimeters, another one next to it that's 2 millimeters. So they're adjacent slices. So it gets 4 slices in one rotation. And then, a certain time interval later, the patient breathes, and then the tumor's down here, and it takes 4 more slices. Okay? Now remember, we're still in this first table position. So these are 4 more slices of the same position, table position, but it's at a different cycle of the breathing cycle, different point in the breathing cycle. Okay? And then the tumor's in another place, and the lungs, etc., all the anatomy is in another place. They take another 4 slices. Okay? And they do this for the entire breathing cycle. Right? So it looks like this breathing cycle has been split up into 1, 2, 3, 4, 5, 6, 7, 8 segments. Okay, so 8 segments correspond to the entire breathing cycle for this patient. And each time we've got 4 slices, so an 8 millimeter thickness. Then once we've got that, we've only got 8 millimeters. We've got to scan more than 8 millimeters, right? So then they increment the table. They probably increment to 8 millimeters. Okay, and then they do the whole thing again. Okay, so then we've got. So after this is all done, we've got 8. We have 8 times more slices than we would for a regular scanner. Okay, because now we're getting 8. We're splitting up the breathing cycle into 8 parts. So we have 8 times more. But now we have a scan that tells us everything about the entire breathing cycle. Okay, and where the tumor is for the entire breathing cycle. Okay, makes sense? So what they've done is they'll monitor the patient, see how long one breathing cycle is for this patient. So if the typical breathing cycle is 5 seconds. Yeah, about 5 seconds. Okay. So they'll take those 5 seconds and they'll split it up into 8 segments. Okay. So each one of these corresponds to a time interval that's 8 seconds divided by, 5 seconds divided by 8. Okay. All right. So, and then how do we monitor that? Well, a very typical way of monitoring that is this infrared camera. So this infrared camera, this is usually mounted near the foot of the table, okay, on the wall somewhere. and then they put a little marker, I don't have a picture of it, but it's a little marker, it's a little block with reflective. You guys know what Scotch light is? It's this reflective material that you see on running shoes and athletic gear. So when a car headlight shoots it reflects it back. Huh?
Your sister's on one.
Oh, she's on that. I'm going to ignore her, it's obvious. So this Scotch light, they put this block with 2 little dots of Scotch light material, and that material reflects infrared. All right, so this infrared camera, so here's the patient lying down on the CT scanner, and we put a block with 2 little dots of this material and this infrared camera with all the little infrared emitters. They illuminate this block, and then this block reflects this material back to a camera. Okay, so there's LED transmitters all the way around it, and then there's a camera in the middle. And that camera, see these 2 little dots? That camera, that image right there is displaying what the camera you can't see, it's this black dot in the middle. It's displaying what the camera's looking at. As the patient's breathing, these dots are going up and down. Okay? So that's how it's monitoring the position of the breathing and the cycle of the breathing. Okay? Then it displays it on a computer screen. So here's the cycle of the breathing, of the patient's breathing. Okay, up and down, up and down. We can display that cycle. Okay. This is a screen cap of the Varian breath gating system. And so now, if we know the breathing now of the patient, now this is for radiotherapy. If we know the breathing, we can say, well, we don't want to treat the entire time because the tumor moves around too much. And if we're going to narrow down our margins, so here's a slice of the patient. Here's 2 lungs, long, okay, and there's a tumor here. Okay, and that tumor moves. It moves in all directions, but just for simplicity, say it moves up and down in this case. And we set up our treatment fields. I need more colors. We set up our treatment fields to treat this thing. Well, it's permanent. I used to have a big box of all colors, and now I'm down to red. Okay, I gotta get some more. But anyway, I'll use guided lines. Say one of our treatment fields looks like that. And this thing, so this is one of our treatment fields from our treatment planning computer, and this thing's moving up and down. Well, in some of the portion, we're going to miss the tumor. Okay, that's not good. So we're going to shrink down our margins, but what we can do with our linear accelerator is we could turn it on at the exact point we want it to. So we've got our 4D CT, and we've taken, let's go back to this. Okay, we've got our 4D CT, and we've taken one of these and we said, we want to treat the tumor right at this point right here. So you have an entire CT scan of this point right here. And actually, that's a really common point to treat, because when the patient exhales, they actually pause for a little bit at the bottom and exhale. So it's a good time to treat. So they say, we want to treat the patient right at this breathing cycle only. Not the entire breathing cycle, only this one. Okay, and that corresponds to this position, for example, of the tumor. And we're going to base all our treatment planning on this scan. This is an entire CT scan right here of one cycle. Okay. So how do we control the linear accelerator? Well, the linear accelerator also has one of these cameras, and it's also monitoring the patient. And so we can tell it, see this gray box right here? That's the treatment box. And we can make that box really narrow. We can scrunch that down to this portion, to just this portion right here. Okay? And once we do that, we're telling the linear accelerator just to treat at that one point. And how does it know? Because it's monitoring, because the linear accelerator is hooked up with to one of these cameras, and it's watching that block go up and down. When that block goes down, it turns the beam on. When that block comes out of this window, it turns the beam off. That's called breath-gated radiotherapy. Okay? So that way we can turn the beam on only when the tumor is in that right spot, the spot where we want to treat it. Okay? So that's called breath-gated radiotherapy. Okay? Okay. So that's, just so you guys know, breath-gated radiotherapy is not very commonly used across the board. because it's still controversial. And it's controversial because you do your CT scan and you acquire the 4D CT, but then you bring the patient to the treatment room and they breathe differently. So you've got this pattern that you've established in the 4D CT, but then they go to the treatment and the breathing is different. And so you have this little window that you're trying to treat through, and then maybe the patient spent a lot of time in that bottom portion when you did the CT scan, but when you treat, they're erratic and they spend very little time in that portion. And so the beam is on very little, and it's very inefficient, and it takes really long to treat the patient. So breath gating is not too commonly used, and it's used in centers. Well, first you have to have the equipment, that infrared camera, the right linear accelerator, and then you have to select your patients that breathe very evenly and are very consistent. Okay, so breath-gated radiotherapy is right now still controversial, and it's still not used across the board by everybody. Okay, but it's a modern technique, and I want you guys to know what it is because it's being used more and more these days. Okay, now image sorting. What is image sorting? Image sorting, there's two ways that you could sort the images from a CT, going back to 4D CT. You can sort the images based on phase-based image sorting, where the images are just sequenced in time. It may not be appropriate if a patient breathes erratically. So that means that the CT scan is just sorted on phase, and it's sorted by time. Okay? The other way you can sort the images is amplitude-based image sorting. Images are sorted based on deflection of marker block. Okay, so now instead of having just a time-based image sorting, you can say all the images that are above this point, where the marker block is in this position, call that a whole CT scan. Okay, and the images that are at this bottom part, call that a whole CT scan. And then you could say, I'm going to treat only on the images that are where the marker block is down at the bottom. Okay, so if the patient breathes erratically, it doesn't matter. They can breathe erratically, but you're taking, for example, you might want to treat in the images that are where the block is at the bottom. So even if the patient breathes erratically, you're always treating in the same position. So this is a little more desirable. Okay. MIP, maximum intensity projection. So what this is, and this is actually probably the most common way of treating patients with breath management. So the maximum intensity projection is, you've got your 4D CT scan, okay, and you can see on the software, it'll show you the tumor movement in a particular slice. So what the physician does is, here's one slice. Here's one slice in time. Okay, so this is time, and time is going to progress that way. Marker, okay. Okay, so we're moving in time. So this is the first one, and then in the next slice, the tumor moves up a little bit. The tumor's a little higher. Okay, and then in the next slice, the tumor's up a little higher. Next slice, the tumor's up a little higher. And then the tumor comes down after the patient exhales. The tumor comes down. So this excursion of the tumor can be drawn in an MIP. So if this is an MIP, the tumor is going to look like this. It's no longer going to look like a snapshot in time. It's not going to be blurred out. So the MIP takes the tumor, actually it takes everything, and it blurs it all out. So now the tumor, what you're seeing, instead of seeing the tumor a snapshot in time, you're seeing the whole tumor blurred out. Okay? Now, once you've got that, this gives you information of where the tumor's going to be the entire time the patient's breathing. Okay? It can move in and out, it can move sup-inf, it can move ant-post, anterior-posterior, it can move left-right. So as you go through the CT slices, you'll see a blurred image of the tumor. Now the doctor can say, okay, I'm going to take this blurred image and I'm going to set on my treatment field so it covers the blurred image, and I'm not going to gate. So this is MIP, not for gating. Not for gated radiotherapy, therapy. Okay, so MIP, maximum intensity projection, is just to give the physician information about where the tumor is in time. And they're going to set up their treatment fields to cover that whole tumor excursion, the whole tumor range of motion, and then they don't have to worry about this. They don't have to worry about all the issues with breath-gated radiotherapy. Okay? But that gives them the information of where the tumor is. Okay, let's take a break. There's a lot of information here. I hope I'm not losing you guys. And I'm giving you an overview. It's important you know all this because radiotherapy has really been evolving over the last few years, and there's just so much to know. And so I try to keep these lectures updated. And well, we'll talk about that next when you guys come back. So was the weekend restful or busy?
Busy.
Yeah.
Busy, yeah.
We hope for it to be restful.
What's that?
Your hope is for it to be restful, but with all the
I know.
activities,
Yeah,
it's not at all.
that's true. There's so much to do these days.
Too much.
Yeah. Are you still involved with your dance troupe?
Yeah. We have orientation next week for new dancers because the season just started.
Oh, okay.
So.
Do you audition?
No,
Oh, okay.
no. But they filter out
Uh-huh.
after they realize either A, they can't keep up, or B.
Oh, really?
Yeah.
So you take anybody that volunteers and wants to?
Yeah,
Okay.
basically.
Mm-hmm.
I mean, I was one of the founders of the whole organization, so we started in 2008, and this year we're introducing a $10 monthly fee, so we'll see how that goes.
To join?
To join. Yeah.
Oh, okay. Are you getting a lot of people? Is that why you're trying to filter some out?
Yeah, I mean, it's a way to, we get sporadic people. It's people that show up, people that don't show up. We need consistency.
Right.
And so by, putting in a $10 monthly fee, we're thinking, okay, who's going to pay $10 if you're not going to be consistent with?
Right. Yeah.
So we're hoping it'll filter out some people who are, they'll show up for, performances, but they won't show up for practice.
Right. Yeah.
So.
That's not good.
No.
If they're not practicing.
Because it's obvious. And we record all the performances.
Mm-hmm.
We just had a big one in Evanston.
Oh, yeah.
And it's obvious who doesn't go to practice.
Was there an Armenian Fest in Evanston?
Yeah, that's where we.
I was at the gym at EAC, Evanston Athletic Club, and I think right around the corner there was a whole bunch of stuff being set up, and I saw something about Armenia. It was on Benson and Northwood Church. Church.
Right on the, exactly. I forgot the name of that street.
It's the corner where there's
Kosi?
That's it.
Yeah.
That's it. Mm-hmm.
Yeah.
Were you there?
Yeah, I performed there.
Oh, okay.
Actually, no, I haven't broken that. I was recording it. Yeah.
You were recording?
Yeah, last year I performed there. Yeah.
What day was that?
Sunday.
Sunday.
Did you finish the homework?
Yeah, I think so.
Yeah, I don't know how to do the last two.
Yeah. So we can talk about it. I'm not too sure what it's about. I do that. Yeah. It's one about the ceremony.
Oh,
When NLC ceremony.
Yeah.
Are you? What am I going to do there? Are you going behind?
No. Are you, Linda?
I don't think so. Ball game is not my favorite thing to do.
What do you like to do?
Sleep.
Oh.
What else are you doing? I'm not gonna
There's that. It's always productive.
The only ball game that I watch is soccer. Only when some teams are playing, I'll just sit for a minute to find the game.
Baseball's a lot more fun to watch at the ballpark than I can't watch baseball.
Well, I mean, isn't the theory that you have to be drunk to enjoy it? Is that
No.
what people drink at the baseball game?
I heard that.
I've never been to one, so I wouldn't know. But that's what I've
That's why you
heard.
should go.
But
See, that's why you should
I
go.
don't know.
So are you all going to Theo's place after?
I have no idea what the plan is. I just said I wanted to go to the game. I don't know.
They're all going to Theo's place after?
That's what they were talking about, right? In the restaurant.
I thought that was just one time.
No, I mean, they were mentioning it like.
Oh, really?
To go there and go.
I don't want to be out too.
Wouldn't that be kind of weird? What do you think?
Yeah. That's why
I wouldn't know how to answer.
you have a long day tomorrow.
Yeah, it is. Always will have a conference. You drove your turn. It's right here.
So shall we meet afterwards? Like right after
Say it one more time.
Oh, it's still recording.
Oh, for that, yeah. Absolutely.
Here they are.
Wow, that's an elaborate box for markers.
I know. Pretty fancy one. Okay, let's keep going. So, we talked about that marker box. So that's one way of tracking breath, the breathing motion. Now, that marker box is outside the body, okay, and we're trying to track breathing motion of the tumor. That's really what we want to track, where the tumor is. But we're actually tracking breathing motion of the outside surface of the patient. So there's a lot of studies that show that we should really be tracking the tumor motion. Okay? And what people do to track the tumor motion is they'll have the patient go to interventional radiology and they'll put a marker, like a metal marker, right in the tumor with a needle. Okay? And then they'll x-ray this tumor during treatment. So that way they can track the tumor. And then what this slide shows is, it shows a couple of graphs. It shows a patient this is one patient, and there's another patient. Let's read the caption here. Comparison of external marker block motion, that's the marker block I talked about, with internal motion of the clinical target volume for a patient with, so now internal motion of the CTV. The CTV, by the way, is the tumor. So we're comparing the motion of the tumor with the motion of the marker block for a patient with no phase shift and a patient with significant phase shift. And what they mean by phase shift is they're breathing one way in the CT scanner and they're breathing a different way in the radiotherapy room. The respiratory gating thresholds are set using the external marker motion. The beam on pulses are highlighted in red over the internal CTV position. Okay? So this threshold, this is where they want to treat between these two lines, and this is the breathing cycle. So if you look at this patient, there's no phase shift, which means the tumor motion matches the marker block motion, and then these black lines is the beam on pulses. So this is beam on is here, beam on is here, beam off is down here, beam on is here, beam off is down here. So we're beaming on between these dotted lines, and the red line right here was again the beam on pulses are highlighted in red. Okay, so this looks like the patient's going to get treated correctly. So we're beaming on exactly where we want to beam, but then if there's a phase shift, it means that the tumor motion is in blue, and the marker block is in green. All right, so the patient's breathing, and the green one is showing the motion of the marker based on the camera. Okay, but the tumor is doing something else internally. Okay, so the marker block may be going up and down, but the tumor might be going sup-inf. Okay, and that's not desirable, because the tumor is moving in a different direction than the marker block. And so what happens is that the computer is set up so that it only treats when, let's see, when the tumor motion and the marker block are doing the same thing. You see how they're both decreasing here? But so the beam is only going to be on for a very short period of time. So in this example here, the beam is on longer than it's on here. So it's going to take a lot longer to treat this patient than this patient. I just wanted to show you that there's a difference between the tumor motion and the marker block. And that's one of the problems with breath-gated radiotherapy. And you could, AAPM report number 91, oh, first of all, that brings me to a point. Are you guys all AAPM members? Student members? Okay. You should all become AAPM student members. Go to aapm.org, aapm.org, not right now, but in your free time. Go to aapm.org and go to the membership area and apply for student membership. And this is our professional organization website, www. Okay, apply for student membership, and then that'll give you access to, first you'll get emails about the meetings that are coming up. It'll give you access to a lot of things on the AAPM website, such as salary surveys, job postings. The publications, I think, are free to everybody. So this AAPM Report 91, you can get on the publications link in there. And these reports are guidance reports. There's a whole bunch of them. There's guidance reports. Actually, one of our the next course here that I teach here is based on these reports, AAPM reports.
Is it free?
I think the reports are free. Yeah.
I mean, the membership.
Oh, I think it's like $25, $30 or something. Okay. I believe you need a letter from us, so just go in and apply, and then let me know what you need, and I'll write you guys a letter. It's just a letter that states that you're students here. Okay. All right. A little bit more on 4DCT. 4DCT. So we talked about 4DCT with that camera that monitors a block motion, and that was called, I don't know if you noticed, but it was called retrospective 4DCT. Retrospective, retro means back in time, right? Before. So what the 4DCT that we talked about before, you take the entire scan, and you take all the breathing cycles, and once you're done, then you could sort through them. You could determine at that point what cycle you want to treat on. Okay, that's called retrospective 4DCT. What's this? Oh, that's okay. Yeah. So that's called retrospective 4DCT. Now, if you don't have a 4DCT scanner, you could do prospective 4DCT. And this is when you're going to use, this is, for example, in our institution, we have a single slice scanner. And we can't do 4DCT because it would take too long, it would burn out the tube, because you're only doing one slice at a time. Okay, so the tube would be on too long and it would just burn out. So at our institution, we have a single slice scanner, so we would have to do prospective 4DCT. Now, prospective means that you still have the camera, you still have the marker block, and what we're going to do is we're going to monitor the patient's breathing, and we can see the little sine wave, the sinusoidal wave, and we can say, well, and we can pick the bottom of the slice, bottom of the breathing cycle, and we say, well, we want to treat at this breathing cycle. So we evaluate breathing before we do the scan. Okay? And then once we do that, so here's the breathing cycle, and it actually usually, if you're an even breather, it looks like this. It's flat at the bottom. So then we set our threshold. So this is even before we start. So this is prospective. Prospective 4DCT. And so we look at the breathing cycle with our computer in our camera, and we have a marker block on, and then we say, well, we want to treat, this is what we want to treat. When the patient gets to the bottom of the exhalation, after the exhale, that's what we want to treat. We set that up. Now, once we start the scan, we could tell the scan to only scan in this part right here. Okay, so they're only taking a scan here, here, here. That's where we're taking the scan. Okay, so we're only going to get a CT scan of this spot, of this spot right here. So we're going to end up with 1 CT scan instead of 8. Okay, and that's called prospective 4D CT. And so people who have a single slice scanner can still do 4D CT, but it's prospective. The only problem with that is that, again, if the patient's an erratic breather, I mean, you might be treating you might be scanning this spot here in one scan, and the patient might be up here. If the patient's erratic, it's a little risky to do.
So why do you fix the breathing of the patient?
You could do that
breathe
too.
In, out, breathe out. No.
You could do that too, and I think we're going to get to that in one of these bullets. I'll talk about that. Okay, so that's prospective 4D CT. Prospective means ahead. You're planning where you're going to do the CT scan, and so the CT scan is triggered. The X-ray, what's this spelling? X-ray tube is triggered. It's triggered at a particular breathing cycle. So as the block goes down to its most bottom position, the X-ray tube does a slice. Okay? And you end up with 1 scan. So prospective CT is 1 CT scan. Retrospective, don't mix these up there. Retrospective is what we talked about before. Retrospective 4D CT is 8 or more scans. Okay. So this takes a lot more data. Okay. 8 scans is going to be a lot of computer data. This is not going to be as much. So this is going to be a lot more computer data. There's also going to be more dose. The patient's going to get a lot more dose with prospective. With retrospective, they're going to get a lot more dose with retrospective. Okay, so more computer, more memory required, computer memory that is, and delivers more dose to patient. Patient dose, which is bad. Okay.
So prospective is better?
Prospective is less dose and less computer data, but if the patient's erratic, you might not have the right CT scan. Okay. If the patient breathes erratic. So you have to select the patient very carefully. Okay, so again, using a single slice CT scanner, the camera monitors the breathing block. The X-ray tube fires only at a particular part of the breathing cycle. Okay, it fires based on where the camera block is. All right. Poor-man CT. Okay, so say you don't have prospective or retrospective, you could still do other things. Okay, so poor-man's 4D CT with a single slice scanner, you could take 3 sets of CTs, and we've done this a few times at Evanston. You could do an inspiration CT, so you tell the patient to breathe in, hold the breath. Then you tell the patient, same patient, breathe out, hold the breath. And then you tell the patient to breathe freely. And you do 1 scan for each one of these. Okay, and then as you breathe in and you breathe out, and you compare the scan, you can fuse all the scans together on the treatment planning computer. And so in one of them, you're going to see a tumor up here, one of them, you're going to see a tumor down here, and one of them, you're going to see a kind of like a blurred out tumor. And that's fine. Contour the tumor, and all 3 then merge contours into one large tumor that has motion built into it. Okay. This is a big problem. We did this a few times. The thing is that the patients breathe in, they take this huge breath, and the tumor's like way up here. And then they breathe out, and the out's not so bad, but the in's bad, because nobody's going to breathe like that on the treatment table. You know, no one's going to go on the treatment table. You know, people are going to breathe regularly. So here we are contouring these tumors of inspiration and expiration, where the tumor's at an extreme point. That's really not. I mean, it gives us a really big margin over which the tumor's going to move, but it's not realistic. So we try that, and it's hard to coach a patient to tell them, you know, breathe in, but not too shallow. You know, it's just hard to coach a patient to do that. Okay? So that's one way you could do breath management radiotherapy. And this does not include any kind of breath gating. It does not include any kind of special equipment. You could do this with a single slice CT scan. Then, the other option is a slow scan CT. And we've done this a couple of times too. This blurs out the tumor motion. The physician can see the whole range of motion. It's kind of like the MIP. Okay, so a slow scan CT, regularly you CT scan a patient and you do a 1 second scan. In other words, the tube goes around in 1 second. A slow scan, the tube goes around in 4 or 5 seconds. So the tube is slowly moving around the patient, and while they're moving around, the tumor's moving. Okay, so you're capturing a blurred out version of the tumor motion. Okay, and that's okay, but I mean, you might be capturing it also depends on where the tube is. So it's kind of, that's not a great way of doing it either, because the tumor might be down here, and so the tube's coming around here, and as it comes up here, the tumor's here. So when it reconstructs it, you don't know if it's reconstructing it down here or up here, or is it catching more of the motion here than it is here based on how it's reconstructing. It's not a great way of doing it either. But it's better than this one. It blurs it out. And actually, I have a little experiment that we're starting to come up with the best CT scan procedure for this, so that you get the whole tumor motion. It's a little study I'm doing. Okay, then what Michaela was saying, deep inspiration hold, monitored by spirometer. So this is another, these are all different options that you can do, by the way. These are not all the same thing. Deep inspiration hold. The spirometer is something that monitors airflow. Okay, so they put this mouthpiece in the patient, and they tell the patient to, first of all, they do the CT scan with a deep inspiration, and they tell the patient, hold it, and they do the scan, and the spirometer is monitoring if they're breathing or not. So if the patient starts breathing, they stop the scan. So that monitors, that allows, that tells us whether the patient's where they need to be in terms of their deep inspiration. Okay? And so, and then we do the same thing for treatment. When we treat, same thing. We tell the patient, hold your breath, and then we're monitoring with the spirometer. If they start breathing, we shut the machine off. The machine actually shuts off automatically by the signal of the spirometer. Okay? But that takes long to treat too, because these patients, their lungs are not in good shape. Okay, so they can't hold their breath very long. I mean, you and I, we could probably hold our breath for how long?
10, 11 minutes.
10, 11 minutes.
I can't do that long.
So,
Less than.
anyway, it's about, we could maybe do a minute, right, if we really had to. These guys can 10 seconds tops. I've seen them when their lungs are in bad shape. So that means that you're delivering a blast of radiation in 10 seconds, and then you have to give them a break and let them breathe and give them another blast. So that takes long to treat too. Who said that? Chest compression. This is another method. So in chest compression, there's a belt that you put around the patient during CT scan, and it's really a bladder, and you can pump it up with air, and you pump it up until the patient is sort of uncomfortable, and that restricts breathing motion. Okay? So you use that, you do the CT scan, and then you treat with that thing too. So that restricts breathing motion. Okay? So those are all the options that we have for breath management, guys. There's a lot we could do. The most common, I would say, is what I talked about, the MIP, maximum intensity projection. People buy a 4D CT. They can see the whole tumor motion. They can advance it in time and watch the tumor move up and down, and then they just draw where the tumor's moving. So most people are doing that these days, and they don't have to worry about gated. A lot of people are doing chest compression. Deep inspiration hold, I haven't heard too much. Some research centers are doing that. And some people are doing slow scan CT, including us. Okay. Next slide, here we go. Calculate the size of 4D CT. So this is just a little exercise. Think about this, guys. I'll let you work on this at home. Calculate the size of the 4D CT image set. Okay, now this is the 4D CT where we took 4 slices per rotation. And an image size, so one slice is 512 by 512 pixels. A CT scan actually has really poor resolution compared to our TVs. Okay, it's only 512 by 512. Our TVs are like 1080 by 1080, or they're a lot more. Some of our computer monitors are 2000 by 2000. Anyway, CT slice is 512 by 512 pixels. 1 pixel, you can assume 1 pixel is 2 bytes. So I'm going to let you guys calculate. I think this is one of the assignments. Okay, so think about how many CT slices you're taking a 4D CT, and calculate the total size in kilobytes. And this is a little movie of gated radiotherapy that we talked about, where the beam comes on only at a particular time. Okay. Oh, maybe this slide should have been earlier. But yeah, this is this is the DRR slice again. This is the DRR topic again. So getting back to DRRs, this slice just explains. This is a DRR right here. Well, it looks like a radiograph, doesn't it? This was acquired from just a bunch of CT scan, one CT scan. Okay. So axial images from CT are used to provide information about the patient's internal anatomy. Attenuation and rays are traced from a virtual source to the patient. The virtual source is the source of X-rays, so the target, that's the virtual source. To create an image that looks like a planar projection radiograph. That looks like a planar projection radiograph. Thinner CT cuts provide sharper DRRs. Okay. Now, remember how I said that CT cuts can be from 1 millimeter up to 5 millimeters? Actually, they can be bigger, but we don't use anything bigger than 5. Most people don't. If you're doing 5 millimeters, each of these, this is one slice, another slice is next to it, another slice. It's going to be kind of blocky. Okay, and your DRR is going to look like Lego pieces. They're going to look a little blocky. Okay, so the thinner the cut, the smoother your DRR will look. Okay. The lowest energy beam is used to provide the best contrast. So a low energy CT scan beam is going to give you a better contrast. And then once you have a DRR, you can impose contours on the DRR. So the physician, after they draw their contours, the anatomical contours on the CT scans, you can look at the DRR and see how they show up on the DRR. Okay. After you stack them all together. And we use this for treatment planning and for making blocks. Okay. Have you guys seen DRRs on the treatment planning computers yet at NIRA? Okay. So it's not totally. Okay, MRI. We talked a little bit about MRI, introduced it to you guys. So just some basic points about it. This is an MRI image. And how can you tell, a couple of things. How can you tell it's not a CT image? Just by looking at it. Do you know? Well, I can tell you. In an MRI, bone is going to be black. Okay? So you see how that's black right there? That's actually a cranium right there. So the bone is black. That's the biggest distinction between MRI and CT. And also, these ridges, you can see a lot more contrast here. Look at the brainstem, it just jumps out at you. You don't see that kind of contrast in CT. Okay. So, excellent soft tissue contrast, great for delineating tumors in the brain, okay, for contouring tumors in the brain. Image distortion. The disadvantage of MRI is that you can have image distortion. And image distortion is due to heterogeneous magnetic fields. And MRIs are acquired from magnetic fields. There's no radiation involved in MRIs. So if there's any distortion in the magnetic field, you'll see the distortion in your image. And you can enhance the contrast in your image by infusing the patient with gadolinium. It's just an infusion contrast agent. Okay, positron emission, just some points on positron emission tomography. It's radionuclide imaging, which means that the patient is injected with radioactive material. Okay, it's infused into a vein, and it goes all over the body. So the patient is infused with radioactive material. The body organs take up the radioactivity, and axial images are acquired by special detectors. And the PET scanner looks like a CT scanner, actually. So the patient goes into the tube, but there's no rotating X-ray tube. There's just detectors that monitor radiation that's coming out of the patient. Okay, and that radiation is used to form. Look at how blurry that is, though. Okay, so this PET scanners are the worst images, the blurriest image. But because you're injecting the patient with radioactive material, this material is now being part of the physiology of the patient. Okay, so what we use PET scans for in radiation therapy is for showing us where there's active tumor growth. Okay, so where there's no activity. So for example, the doctor will look at a CT scan and they'll see tumor on a CT scan. Okay, and that's just because it just got denser. Okay, so remember a CT scan shows you density. It just got denser. But how much of that tumor is active growth? Okay, so that's what the PET scan is going to tell you. So the PET scan will show you some of the tumor, but the parts that are highlighted the most, that's where there's most active tumor growth. That's where there's most metabolism going on. Okay, and the doctor needs to know that because they might want to deliver more dose there, that part there. Wow, where are you going? Okay. That's part of the other slide. Okay. So here's a comparison of all three modalities. How many more slides do we have?
There's 33, I think.
33, okay. So this is just a comparison. 10 more? Okay. CT scanners. CTQA, one of the task groups, you know the reports that I was telling you about? TG66 is one of the report numbers, and that goes into quality assurance and CT scanners. But anyway, the properties of CT, geometrically accurate. That's the most important part for us. We do all our CT planning, our treatment planning based on CTs because they're geometrically accurate. High density structures are highly visible, so high density, so bone is highly visible on CT scanning. Iodine-based solution is infused into the blood to enhance contrast. So if we need to see vessels, and in the brain, for example, they'll infuse the patient with an iodine-based solution. Iodine has a high Z. Okay, so if we do a CT scan, we'll see that very clearly. X-rays are typically 130 kb. We use CT scans to contour the patient's external surface. Remember how I said it's important to see the external surface for calculation? We need that. Electron density information is used to correct for heterogeneity in dose calculation. So when we're calculating dose, the photons will get through air easier than they'll get through bone. Okay, so we use the CT scan information to give us that information about air versus bone versus soft tissue, and so we can calculate our dose more accurately because if we know what the difference in density is. Okay, so those are the main points of why we use CT scans in radiotherapy. An MRIs could possess geometric distortion due to the magnetic fields as I just described. Excellent soft tissue contrast enhanced with gadolinium. Okay, we already talked about that. And PET, so this is one of the chemicals they use, FDG. Areas where active cell division is enhanced, shows organ function and cancer cell activity. Okay, we already talked about that. And then here's image fusion. So we have all these possible modalities, and all these scans can be sent to our treatment planning computer. But once they're sent, what do we do with them? Well, we have to fuse them. We have to put them together so that we don't have a CT scan here and PET here. Obviously, it's more useful to us if they're fused together. And so, how does fusion work? Have you guys seen fusion in the clinic yet? So with fusion, we'll take an MR, and on the screen we can kind of move it around and align it. Okay? So we can align the CT and MRI. And then we can do the same thing with PET. We can align the PET image to the CT. We can perform fusion. There's some transparency so we can see through it to help us fuse. And these days, the fusion that we do is all automatic. Okay, fusion's there's algorithms in there that do automatic fusion. And so this is what a fusion result would look like on a screen on our treatment planning computer. We fused an MRI to a CT. Okay, and you can't see too much common. You can see a ventricle here. This black part here is a ventricle. It's fluid filled, and that's overlaid on this ventricle. We can move this window around to evaluate how good the fusion is. Okay. And so the purpose of fusion is the physician, say you can't see the tumor on CT, but you can see it on MR. So the physician will go into MR and draw the tumor with the mouse on MR, and then we don't look at the MR anymore, then we do all our planning based on CT because it's geometrically accurate. PET CT. So these days you can buy scanners that are PET CT built into one. So the fusion it's inherently fused. So PET CT fusion is error prone due to poor image resolution of PET. So if you had a PET scan that came from one site and a CT scan that came from another site, and you tried to fuse it, it would be very hard because it's so hard to see anatomy on PET. So a PET CT allows you to fuse it inherently because the patient gets a CT scan and they're in the same position, and then they get a PET scan. They just keep going further down in the machine. Okay, so there's been a lot more PET scanners in the industry. Don't need to fuse it. Enhancement in PET usually points out active tumor growth. We already said that. Lymph nodes. So PET gives us information about lymph nodes. Yeah, so the problem with PET scan is that to take a PET scan, it could take 45 minutes. So the patient can fidget in those 45 minutes. So that's a problem with PET scanning. All right, and that's what a PET CT, that's a terrible image. But anyway, that's what a PET CT looks like. Couch, this part right here would be a CT scanner, and this part back here would be the PET scanner. It's all in the same unit. And here's the results you get. So this is a coronal. Remember what you guys what coronal is? Coronal is a cut in this direction. Axial is this direction, and sagittal is this direction. Okay, so this is a coronal cut of a body, and this is a CT, reconstructed from a CT scan. Here's PET. Notice how PET gives you very little anatomical information. And what I mean by that is, over here you can see ribs, you can see heart's right there, you can see the lungs clearly, you can see other organs, you can see the liver right there. Okay? In PET, you don't see much of that. Okay? So when you're making diagnoses, it's difficult to do that just with PET. But when you've got a PET CT, put them together, and there's the enhancement in PET here and down here, and you can overlay it on anatomy.
Where does the color come from?
The color just comes from the software. You can pick whatever. You can pick orange, green, whatever color you want. But what's important here is what's enhancing. You know, what's bright and what's not bright. Okay. Oh, shoot, some of these are out of order. The portal imaging should have been back when we were talking about portals. But this is just a repetition of what I said before. Radiographs are taken before treatment. So these radiographs are, these portal radiographs are taken on the first day when the patient, after the treatment plan is done, the patient comes for treatment, and you take the radiographs. And the double exposure is, on that slide that we were looking at, we had a double exposure portal radiograph. So the first exposure of a portal radiograph is large, so the jaws are open, and I'm going to use the pelvis because I can kind of sort of draw a pelvis. Okay, issue of tuberosities, the sacrum. So that's the first one where you see the whole anatomy, and then the second. So this is first exposure. Second exposure is you bring the MLCs in. Okay, so then the second exposure will show you the blocks, whatever blocking there's been on this patient. Okay, so in the second exposure, you'll just see this part right here. So in the dual exposure radiograph, you'll see all the anatomy and then with the blocking overlaid on it. If you only did one exposure with the blocking, obviously you want to do the blocking because that's one of the things that you're checking when you're doing a port film. So if you just do the blocking, then you wouldn't see anything behind the block. Okay, and that might be a problem if there's a lot of blocking, you don't see much anatomy. So the double exposure lets you see through the block. So the purpose is to verify patient position with respect to treatment field and MLC blocking compared to simulation films. We already talked about that, or DRRs. Portal radiographs are taken with film or with EPID. You guys heard of EPIDs? Electronic portal imaging device. So when you look at a linear accelerator, most linear accelerators have them. I mean, when I talk about portal radiographs, I meant film, but these days we don't use film. So I'm going to draw the gantry here. There's a gantry head. So if you look at a gantry, any gantry you look at, you'll see this little section right here, and this is an arm that swings out. And the patient would be on the couch here. Here's the couch, and then the patient would be here. And then there's an arm that swings out of here, and this is an amorphous silicone digital plate. Okay. Okay, the patient's not this close to the gantry. But anyway, the photons come down, and then you can take an image of the patient, and that image is relayed to a monitor outside on the treatment console. So this is for MV imaging. EPID is MV imaging for portal radiography. Okay? So MV imaging for portal radiography. And again, what's portal radiography for? What's the purpose of portal images? To make sure what? And what are we looking at? Placement of the isocenter with respect to anatomy and verify the MLC and beam shaping. Make sure the blocks are correct. So that's what the Epic does. Patient's in treatment position. It doesn't have to only be AP. It could be at any angle, whatever angle the beam is at, or whatever angle the treatment field is at. You take a portal radiograph, double exposure, check your isocenter, check your blocks. So that's the purpose of an electronic portal imaging device. Next time you guys are by a linear accelerator, ask Athea or Jug to show you how that comes out. So there's several types. These days, you probably don't have to worry about these anymore. These are kind of outdated, phosphoplating camera. These are the most common today, the amorphous silicon plates. So the advantages, mounted on an arm or removable unit, it speeds up, you don't have to process the film, so there's no films anymore. The radiographs can be made available over a network for physician review at their leisure. So after you take this portal radiograph, it's sent to the database, patient database, and the physician could be at their desk. They can pull up the sim film, and they can put up the portal, and they can say, well, it looks like the patient's isocenter is off by half a cm. Make that correction on the next fraction. And then the therapist make that correction on the next fraction. Okay. So the physicians review these films, and the therapists make these corrections. Okay. And it can actually be used for dosimetry purposes too. So that's a newer thing. So it can be used to measure patient dose, as well as just take images. Okay, IGRT. So this is another topic. I told you we're going to cover a lot of topics. And it's all kind of the same thing. It's all imaging stuff. Okay, so IGRT. We're going to do this quickly here. Image Guided Radiotherapy, very common today. It's been, it's probably been MV imaging. You could do IGRT with MV imaging or KV imaging. The MV imaging IGRT has probably been around the longest. And then KV imaging came around after that. So the purpose of IGRT is to image the patient before every fraction, and it allows the therapist to position the patient for treatment based on that day's internal organ position. Okay? So what that means is just before the fraction, we take pictures of the patient position. And you compare those pictures to DRRs, which is where you want the patient to be in terms of the isocenter. Now you're just looking at isocenter placement for IGRT. You're not looking at blocks. And then if there's a difference, you move the couch and you move the patient to that position. Okay, that's what IGRT is about. Before every fraction, you take a picture and verify position. And this can be accomplished with 2 orthogonal radiographs. And you can either locate markers, fiducial markers. Fiduciary markers means markers you can trust. So in radiotherapy, there are usually high Z markers like gold, or usually they're gold markers that are placed inside the organ that you're trying to locate. So we'll place them in a prostate. We'll put 2 linear markers inside the prostate with needles. I don't do it, but the urologists do it. And then we locate those with KV imaging. So we locate either markers or we locate bony anatomy. So we'll locate cranium, pelvis, spine, that kind of thing. So the radiographs that we take may be MV or KV. KV is much sharper due to the better contrast. Okay? Or we can also do cone beam CT. Cone beam CT is what you're doing is, instead of taking an AP and a lateral radiograph, you're rotating the imager all the way around the patient, and you're getting a CT scan every day with the treatment machine. Okay, remember, this is when the patient is on the first day, or actually every fraction, and you're imaging the patient. And so we could do a CT scan every day, and we do. For head and neck patients, we do CT scan every day, and we compare the CT scan that we do on the treatment machine to the CT scan that we had originally. We look at the position, we compare. So you could do, again, you could do 2 orthogonal radiographs. You could do cone beam CT if you have the equipment. Or the other thing you could do is ultrasound. Right? So for prostate, you can place the patient on the table and ultrasound the prostate. So you take an ultrasound probe and you put it on the guy's belly and you image the prostate. So you take a 3-dimensional image of the prostate. And then you compare that to the original ultrasound image that the patient had. So that's another modality. And then you can see where the prostate is and move the couch. The different ones are VAT, Restitu, and I-beam. Those are the different companies that make them. And then another digital choice, there's so many choices. Another digital choice is Kodak RT2000. And what this is, it's just a replacement for film. So instead of using film, you use a cassette, and you image the cassette, but then once you open the cassette, you don't have to process it. You can put it in this reader, and it reads it. And that's how you get your two orthogonal radiographs. This isn't around anymore, but anyway, that's what that is in case you come across it. Another one that's not very common is CT on rails. And what this is there's a CT scanner inside your radiotherapy room. Okay? So you bring the CT scanner around the patient, you just do a CT scan, and then you bring the CT scan out and you treat the patient. Okay, after you've determined the position of the organ. So those are all the different options of IGRT. And then here's why we use IGRT. This is a sagittal cut of a patient's abdomen. Okay? And the doctor's drawn prostate here, and this blue thing is a margin around the prostate, this is bladder, and this is rectum. Well, look at this right here. This is a whole bunch of gas. Okay? Now, what happens when that gas, and this is how we did our CT scan, what if that gas moves down and comes into this position? That gas is going to push the prostate anteriorly. Okay? So say we do this treatment plan, and we concentrate all the dose nice and tight around this blue contour. And then this guy's got gas, and it pushes it up. What's going to happen? And here's another image of that in an axial view. So here's where the prostate, by the way, these are femoral heads, pubic symphysis, this is the acetabulum, the rectum, and the prostate's right here. So right now the rectum's empty. But if it's full of gas or fecal matter, we can push this completely out of the field. So if you think that say your prostate's right here, and you've calculated your dose to be conformal around the prostate, so the red line represents a certain isodose, a certain level of dose. But then the guy's prostate moves, and it's up here. Your dose, it's not going to follow it, because your dose is based on the machine's isocenter. It doesn't move relative to the room. So your dose is still going to be down here. So if the guy's prostate moves out, you're not going to treat this part of the prostate. Okay? And you might treat some rectum down here, which you don't want to treat. Okay? So your dose is based on, your dose is based on the linear accelerator. So this isodose bubble is is set in the room. Okay? Because it's set based on the isocenter of the machine. But the guy's prostate can move. If he has gas, it can move. Okay, that's why we need IGRT. Because if we could have, I think there's another good slide here. Do I have a slide with some markers? Yeah, I do. So this slide here shows markers inside the prostate. So we place these markers inside the prostate, and then if we can image those markers, that tells us where the prostate is. So if the prostate moves up, then the computer tells us that we need to move the couch down. Okay? So then if we move the couch down, the prostate drops back down into the isodose bubble. Okay. So this slide just shows you the linear accelerator. Here's the EPID I was talking about down here. This is and this is a KV imaging system. These two pieces right here. This is an X-ray tube, and then this is a digital imaging plate. And so these are the different parts. So this is low energy imaging X-rays. This is a low energy X-ray tube, and these are the X-rays we use for IGRT. And then this is a high energy MV beam, and we can use this for MV imaging. Okay, there's an imaging panel here, imaging panel here. And the information from these panels are all relayed out to the control console where the therapist side. Okay. A lot of technologies in this machine. The MV imaging will tell you information about isocenter, and it'll also give you information about blocking, because the blocking is all done up here in the head, right, the MLC. This imaging system will not tell you anything about blocking, because the blocking is up here, it's not here. This imaging system only gives you isocenter position. It only tells you if your patient's positioned correctly. So this is for patient positioning. This MV imaging is for patient positioning and blocking. Okay. And this is sharper, it's clearer because it's low energy X-rays, and this is blurry because it's high energy X-rays. Okay. So again, the patient has an X-ray taken before every treatment to establish and correct their position. IGRT may be based on implanted metal markers, such as these that you see here, or bony anatomy. If they don't have any markers, we could just align the bony anatomy. And that's it. That's enough, huh? We covered a lot today. I'm telling you guys, there's more and more to learn in this field. Any questions?